Hey guys, it's Sam here. Happy Friday! How's your day coming along? So today we are going to be undertaking the mammoth task of deciphering a scientific paper. It's related to the COVID-19 virus. So yeah, there's a lot to cover, and hopefully we got some good news at the end of it. Okay, so let's hop along, okay, because we've got a lot to cover. So firstly, shout out to Andrew. Thanks for bringing this paper to my attention. So this was published just 2 days ago, okay, 6th of May, by a group from China. They're based in Beijing. You can see all their credentials here. Okay, so yeah. Anyway, we don't need to go too much into that. But basically, what we're going to be doing today is I'm going to be going through and explaining the paper and what it means. Okay, so why should you be interested in this paper in the first place? Okay, so what this group did is they have potentially found a vaccine. Okay, it's a candidate for a vaccine. Okay, obviously for COVID-19. Now, if you are familiar with scientific papers, you will know that there is a certain style, a certain way that they are written. So yes, I get it. It's very daunting, to come in here and you see this wall of text, and it's not just any text, right? It's texts that have characters more than they're made up more than 7 characters, big words basically. So, like any article, any essay that is good, this paper tells a story. Okay, so that's what we're going to be talking about today, the story of this group, okay, that found the vaccine. So, if you were reading a book, if you got a novel and you flip it open, what would you expect to find at the start? So, you would expect to find the table of contents, right? And then, maybe a preface, a foreword, right? So, if you are reading a novel based on a scientific paper, when you open the book, the first thing that you will read is a synopsis. That's right. You would see something that looks like a Wikipedia page. It will summarize the whole story for you in a couple of paragraphs. That's what this is. Okay, so scientific papers are unique. They have this thing called an abstract. Okay, so if you don't have time to read all of this, or you're not really that interested, you just want to know whether it's worth your time, you read the abstract. Okay, so it's like I said, if you're interested in reading a novel, you pick it up. You're like, should I read this? You go and check the Wikipedia page. You read the summary. You're like, nah, don't really like it. Throw the book away. Okay, but if you do like it and you want to find out all the nitty-gritty, juicy detail, and that's what this is for. Okay. All right. So this paper, the story of this paper, begins with a virus, COVID-19 virus. Okay. Ooh, okay, so yeah, obviously I'm not going to be going through all the text, right? I'm just going to show you the results and explain it according to what they've written. So I should mention that obviously, what I'm saying now is, largely my interpretation of this paper. Okay, so take it as you may. Okay, just letting you know. So as you can tell, they crammed a lot of data into this I guess a bunch of charts. Now this is not the only one. So there's 4 sets of charts in this paper. This is the first one. Okay. So again, it tells a story. So we'll start at the beginning. Start with A. Okay. You see A, B, C, D, E. I'm not going to cover all of it, but let's start at the beginning. So what is this? What is this thing? A circle with regions. Ooh, these look familiar. Okay. So this is a phylogenetic tree of the COVID-19 virus. What's a phylogenetic tree? Okay, it's basically a family tree. Okay, so this is what it looks like. This is a family tree for another virus. Okay, so this is the origin of the virus. The papa and the mama, kind of. But obviously, this is just putting it in human terms. Viruses, like with any other organism, they change over time. Okay, evolve if you like. So they mutate, they change, and across the scale of time, like a family tree, they have kids. The kids are slightly different. Some turn out like this, some turn like this. Okay, and they've been marked to different colors because they're from different regions. Okay, and I'm sure they have slightly different properties, but they can all be traced back to the origin. Okay, family tree. So this is what a family tree, a normal family tree, will look like. Okay, but once you start getting to a larger scale, like this one, then it starts to look like this. All right, then you put it in a circle. What is this? This is the phylogenetic tree for the HIV. Okay, that's the human immunodeficiency virus. You know, the thing that caused AIDS. Yeah. So it's been studied quite a lot, and they found many different subtypes. So that's what the different colors mean. Okay, but as you can see, they all kind of stem back from here, the center. Okay, so this was the predecessor, the precursor, the forerunner, whatever you want to call it. Okay, Papa Mama. Okay, so you go split, split, and they keep splitting. Okay, and they split into different colors. Okay, so these are the different types that exist now. Okay, so if you zoom in, obviously they all each got their own little code, a name, right? But all you need to know is that they all fall under this same little family, happy little family of HIV. So it's the same for this. See these lines? In here is a web of COVID-19 viruses, of coronaviruses, right? Wherever they came from. So what they've done is they've marked the ones that they've isolated. So there are many strains. In case you didn't know, COVID-19 has many different strains because it's a virus. It replicates very fast. It mutates. Lots of different kids that are slightly different from the parents. Okay, there you go. So that's what it means. And all these are just codes of different strains. Okay, so and these strains were isolated in these different regions of the world. Okay, so what these guys have done is they've taken this particular strain, the CN2 of the COVID-19 virus. Okay, and they're going, okay, we are going to focus on this one. Okay, and this is where it occurs. See the black line? This is tracing it back up the tree. Okay, so what this means is this is the beginning of the story. This is the virus. This is the virus we're going to fight. How we're going to fight it? How are we going to fight it? And hopefully, when we successfully fight it, it will hit all these guys in black. In theory, okay. So it may cover more. It may be the vaccine that comes out will be effective against all of these, or it may not. We don't know. Only trial and time will tell. Okay, so that's all this means. It just means we are, these scientists, they have done the vaccine based on, this particular strain of the COVID-19 virus. That's all. Okay, move along. So they detail. So I added in these titles just so that it makes a bit more sense. So they detail the process of creating the vaccine. So what is a vaccine? That's a good question. A vaccine is basically something that causes your body to have an immune response, that your body will mount a defense against, right, without killing you. Okay, so if I wanted to, I could just, instead of a vaccine, I could just give everyone, the COVID-19 virus, but that wouldn't end very well because that's the same as me catching it from, some stranger, or, why would I need a vaccine that could kill me? Okay, so the vaccine should be safe, okay, but still be enough to challenge your body to have its own immunity. That is what we want. Okay, so that is what a vaccine does, and here is how they make it. Okay, so they start with a virus again. Okay, they just forgive the spelling a little bit, but so they start with the virus, they isolate the virus, they grow it, have lots of virus. Okay, now that we have the virus, we need to inactivate it. Okay, so what does inactivation mean? It means they power it down. They knock it down so that if they give it to some other living organism, it won't damage, it won't kill them. Okay, but it should be enough of a pathogen, enough of a virus still, that it will cause the organism, the host, to have an immune response. Okay, so you got to strike a balance. Okay, so this is what inactivation is. Okay, there are many different forms of inactivation in different vaccines. So what these guys have done is they've used this chemical called beta propionolactone. Okay, they added the I in there. Okay, so all you need to know is this chemical is used to disinfect. It's a sterilizing agent, sporicidal agent. It kills microorganisms and spores and stuff. Okay, so definitely not good stuff. Okay, and it's been suspected of causing cancer, carcinogenic. So again, it's not a fun substance. Please don't go drinking this stuff. Okay, it's only used for making the vaccine. Okay, so what they've done is they've used it, they tested it on the virus, appears to inactivate the virus. Good. Okay, so after they inactivated it, next they purified it. Okay, so they need to make this vaccine. They need to make it into a form that they can pump into an organism, right? And it won't give them cancer or any other funny thing. All right. So basically, this is a simplified process. So I'm not sure how long this took them, but yeah, definitely these scientists they're showing that what they've done, and they're showing their secret formula. This is the secret ingredient that they use to inactivate to make the vaccine. Okay. And then after that, they do a few steps. You don't have to worry too much about it, but it's basically they're replicating it, they're making more of it so that they have enough to test. Okay, now next question is how are they going to test it? Well, of course they have to test it on a live organism, right? And of course, who takes the cake? This guy. Good old lab mice. Okay, so they tested on mice, rats, the usual lab rats. Okay, lots of them, and they're mammals, not too far away from us, and there's lots of them. And their body's immune system not too far from ours. Okay, so basically, yeah, that's what they did. Next step, number 2, in mice. Okay, so what they did is, now that they have the vaccine, they pumped it into different groups of mice. Okay, so yeah, there's a lot of charts, but all you have to do is you look at these different colors. So each of these colors represents a group of mice. Okay, so they gave different doses. That's all this means. Red, high dose. Blue, medium dose. Purple, low dose. Sham, gray is no dose. Okay, placebo. Okay, because you have to have a control group. Okay, so what are they testing? Think about it. Okay, you know what a vaccine does. Okay, so what does a vaccine do? A vaccine causes an immune response in the recipient. Right, so if you get a vaccine, you should have a response. Your body should respond to the vaccine. And how does it respond? How do we test the response? Antibodies. See this? So this says SARS-CoV-2, which is the COVID-19 virus, specific IgG. Now, if you remember from our immunology talk, IgG is immunoglobulin G, a antibody, one type of antibody. Okay, so this antibody is specific to COVID-19. Okay, so what do we expect? If I give you the vaccine, I expect you to have immune antibodies to the vaccine, to the COVID-19 virus, right? So that means levels should go up. Okay, that's all this means. Okay, over time. So as you can see, these are week 1, 2, 3, 4. So it takes a while, right? Because bodies take time. You have to eat, sleep, rest. Okay, and so what does all this mean? Results are good, because what is shown here, if you can see, the red, the blue, the purple, the levels go up. Okay, if you look closely, there are no gray levels, right? Because why? Control group didn't get any virus. They didn't get any inactivated virus. Okay, that's what the vaccine is. Whereas these other lines, yes, they got some amount of inactivated virus. So maybe the ones that got low dose may have a slightly lower response. Who knows? But yes, so basically all this is showing is that there was a significant increase in the mice in their COVID-19 antibodies. So good news. It looks like the vaccine is working. Okay, that's all you need to know. And these are just different levels. Okay, so yeah, I won't go into too much detail. And they compare it against the antibody levels in humans. Okay, that's all this really means. Okay, so good news. It works in mice. Conclusion. Okay, antibody levels up means immune response confirmed in the vaccine. Okay, so what is next? So mice works. Next, we test it on something a bit closer to us. Monkeys! Okay, so this is a rhesus macaque. Okay, yes, it's monyet basically. So yeah, hey, random aside, we have a lot of these in Malaysia. And, oh wait, graphic warning, graphic, okay. They have found in Malaysia recently that these macaques, pigtail macaques, so same but slightly different, these macaques have been caught eating rats on palm plantations in Malaysia. Okay, And apparently these macaques quite like them, because they've been eating so many rats that the palm plantation owner has gone, oh, hey, I don't have a rat problem anymore. I don't have infestation. I don't need to call the pest control. Thanks. Thank you, monkeys. There you go. Yeah, just a random aside. So yeah, this is Malaysia. And I don't know, I just made the connection. Rats, monkeys. Okay, so anyway, back to the topic. These monkeys are suitable candidates because obviously genetically they're a lot closer to us. They're you know, the immune system, their organs, very close to humans. So non-human primates. Next step, let's test them. Okay, ooh, this is chart number 3. Okay, so clearly a lot of stuff. Yeah, I'll break it down for you. Okay, so the top one refers to the levels of antibodies in the macaques, in the monkeys. Okay, so again, high dose, low dose, no dose. Okay, and good. So 7 days, 14 days, 21 days, a few weeks, they see the antibody levels of the IgG in the monkeys going up. Excellent stuff. Vaccine is working. Okay. So now they take it one step further. So now that the vaccine looks like it's generating antibodies, right? Now we challenge it. We challenge these organisms. What does it mean to challenge them? Okay, in immunological terms, it means you have the actual virus. Okay, you see this big red arrow, infection, infection. Okay, so that means that they gave the live virus to these monkeys after they were given the vaccine. Okay, so this tests whether the vaccine is effective. Okay, so what would you expect to see? So what you would expect to see is, in the control group, obviously they'll get the full-blown viral infection. You know, maybe they'll start having fever and start coughing. Maybe they won't, because you know, they've shown that in dogs can catch COVID-19, but they don't show any symptoms, not like us. Okay, so whether or not they show symptoms, who cares? This is science. We're gonna measure it. We measure it with these. So this is the viral RNA load. So this is measuring how much virus is in the tissue of the monkeys. Okay, so they swabbed different parts of the bodies, throat, the bum, and their lung. Okay, throat, bum, lung. Okay, and they took the tissue and they tested how much viral load is in there, how much virus is there, because presumably, if your body has an immune response to the COVID-19 virus, there shouldn't be a lot of virus there, right? Because your body's going die, 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 pew, pew, pew. Okay, so you're just left with like dead virus, not live virus. Okay, so viral RNA means live virus. So what they found is, see, green placebo, and gray is the sham, which is the no dose group. Okay, so they gave them COVID-19, and look at that, higher levels, green and gray. Very high, means they had a lot of virus in their bodies, okay, in the lungs, okay, different parts of the lung. Whereas the guys that had the vaccine earlier, a few weeks earlier, all good, lower, much lower, definitely, significantly lower levels of virus. So good news, it looks like the vaccine worked, number one, and number two, it protects against COVID-19. Excellent stuff, excellent. Well, the story is coming along very nicely. Looking like a Hollywood ending. Okay, so now we move on to the next step. What? There's more? Yes. So they in order to validate their results, they took some lung tissue samples of the different monkeys in the different groups. So on the left is the group that didn't get any vaccine, the poor saps. Okay, on the right, different dose of vaccine. Okay, inactivated virus. So as you can see, I won't go into detail. H&E is basically it's a type of staining, so that's what causes the pink and purple appearances, because normally this is not the color that your tissue is. Okay, so they took a bit of the lungs, they stained it. All you need to know is this is what healthy lung looks like: lots of space, room to breathe, you know, in the cells, because it's cellular level. And this is not good, full of crap, pneumonia. Okay, so this is lung tissue, bad lung tissue, full of crap. Lots and lots of crap. Okay, mild pneumonia, normal. Okay, so looking good. All right. So final step. What is the final step? Okay, so the final step is to determine if the vaccine itself is safe. Okay, so that's what this is. Okay, so these charts measure a different thing from the previous ones. They're not measuring antibodies, they're measuring cytokines. Okay, so this top section measuring different cytokines, and the bottom part is again lung tissue. So healthy looking lung tissue in the placebo. Okay, no vaccine, a little bit of vaccine, looks the same. Good news. Okay, so these are just people. These are just the monkeys that got the vaccine, didn't get the vaccine. All good. So what they did is they got different groups. I presume a fresh batch of monkeys, and they vaccinated them 3 times over the period of a few weeks. So 18 days at -1 at 18 days and at 29 days. 3 doses. Okay, and after each dose they tested them. Okay, so I should explain what are cytokines. What does this mean? Okay, so cytokines are these guys. No, not the big blue things. The blue things are your cells. These little grainy salt crystals coming out. Okay, these are cytokines. So cytokines are a group of proteins that act as communicators between cells. Okay, because your cells, they can't make noise, right? So in order to talk to each other, to say maybe this cell is going, I'm not feeling so good, guys, be careful. Okay, so what it will do is it will release these pink cytokines that will travel to nearby cells, and these other cells have receptors for these cytokines, and they'll go, ooh, I'm getting a transmission. Oh, my friend over there says he's not feeling so well. Guys, defenses. Okay, so cytokines are these little proteins. Okay, here's a bit more detail that are secreted, released by your cells to tell other cells to do shit. Okay, they're your body's way of communicating with each other. They're like hormones, pretty much. It's just they're released from different places and they have different functions. So cytokines play a very key role in your immune response, inflammation, in defense, that sort of thing. So by measuring the level of cytokines, it is determining whether your body or these monkeys are having immune response to the vaccine. Okay, not the virus, the vaccine. Because remember, this last part is making sure the vaccine is safe, right? So, like with the flu vaccine, when people receive the flu vaccine, there are complaints that you get mild flu, right? It has been shown that you do get some flu-like symptoms, but you don't get the full-blown flu, right? Because that would just defeat the purpose of the vaccine, right? But you get some mild flu. So what that would mean is if we did this test with the flu virus, you would see a rise in cytokine levels. Okay, they will go up because that means your body is still attempting to fight. Okay, it's showing signs that it is fighting off an invader. Okay, and so in this case, it doesn't look like there has been a significant increase in cytokine levels, which is strange. I mean, good, but yeah. So that means there's no the vaccine itself doesn't have a very strong immune response in the recipients. So it's good enough to generate antibodies, to generate immune response, but not so much so that it causes your body to undergo an inflammatory, full-blown immune response. Okay, roughly, yeah. Okay, so the long and short of it is that it is safe, and it looks like we have a vaccine. Good news. Why is this syringe empty? Anyway, okay, so that's pretty much the conclusion. Okay, so they've shown that this vaccine is safe in mice, it's safe in monkeys, the vaccine itself doesn't cause any problems, and it defends against the actual COVID-19 virus. Good news, guys. It looks like this might be a good candidate for a vaccine. Okay, but we're not there yet, because of course we have to test it in human trials. So they've already done the mouse trials, they've done the monkey trials. Next step is you can start testing on humans. Good news, guys, good news. So yes, we have the workings of a vaccine. Okay, that's pretty much the story. Okay, so there you go. You have successfully survived a scientific journal, a scientific paper. Okay, now on to another bit of news. So there was another paper published also just yesterday. about COVID-19 and this drug. Remember the one that Trump went, "Oh, it's gonna be a game changer, and we're gonna be awesome because America, I said it." Well, sorry, dude. Here's the paper. Okay, published. And ooh, you can apply your newfound knowledge. See, abstract. Oh, these guys even broke it down into different sections. Okay, and then the wall of text. Oh my goodness. Blah 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 blah. Okay, so if you have time, you can go and read this one. I'll chuck the links in there. But basically, this one shows that that hydroxychloroquine, the drug I was just talking about, doesn't really do much. Okay, that is the abstract. See, in one sentence, hydroxychloroquine has been widely administered to patients with COVID-19 without robust. Again, like I said, you can go through it, you can read the methods. So what all this is, the full story is for people who want to replicate it. Okay, so say I read this and I go, no, that's bullshit. I believe hydroxychloroquine still has an effect. So I would learn from what they've written, like just now, and I would do my own studies. So I could take that paper for just now from Beijing, and I could get my own mice and my own monkeys and make my own vaccine, right? And pump them full of my own virus, right? And test whether what they done, whether it's replicable, whether it works. And that, my friends, is the scientific method. Okay, so just because some guys from God knows where say that, you know, this thing is a good vaccine, this thing works, here's our results, don't take their word for it. Okay, so even if they were published in papers like Science, they could be wrong. There could be something that they overlooked. Okay, so this is for it's a form of sharing. Okay, so yes, we can start human trials, but at the same time, we should repeat these experiments to make sure that, you know, that beta propionolactone actually inactivates the virus, that, you know, this particular strain is, you know, worthy of making into a vaccine, you know, and has shows effects against the COVID-19 virus, you know, things like that. So, you know, that's what science is all about. Okay, so people will repeat this over and over again. Different people may see different things, but hopefully, you know, in the long term, the truth will stand out. Okay, so again, I'm not saying that, you know, that we shouldn't try and, you know, do more testing on hydroxychloroquine. Even these guys say it, you know, it requires more trials are needed. Okay, but this is what they see. For now, they don't see any effect. There you go. So I hope you've enjoyed this little foray. I hope you found it enlightening, if not mildly entertaining. Not entertaining, yeah. But yes, so there you go. That's a story in a nutshell. And overall, good news. We may have vaccine, but, you know, human trials, like I mentioned, like you saw just now, each of these graphs is a span of a month, right? So that means it probably takes like a month and a half, you know, 2 months to get all this, you know, the results. We gotta, you know, it's a lot of work. You know, these guys have to measure, they have to take samples, they have to stain. All this takes time and energy, right? And these guys did it like 4 or 5 times. Okay, so that's like a, you know, a couple of months, which makes sense. You know, they started back when this whole thing broke out, the start of the year, and they published the results now, 5 months down the track. Okay, so imagine if they had to do the same thing for human trials, which probably take longer, right? Because you got, you know, the humans aren't just sitting around in cages for you to inject them, you know, with all this crap, right? You got to make sure firstly that it's safe, and then you got to call people to come in and be like, "Hi, would you like some vaccine?" You know, and yeah, and then you know, they got to come back and you got to take the test results. It's a lot of work. So human trials, don't expect it anytime soon. Okay, it's going to be at least another few months, if not more. Okay, so yeah, sorry to throw a bit of cold water on it, but you know, it's a good news. It's good news, right? So we're getting there. We may have a vaccine soon, but in the meantime, stay safe, stay where you are. Okay, and of course we must not forego our Korean Hokkien lesson. So what is today's? Oh yeah, I already had an animal fact with the monkeys. Yeah, that was all part of the plan. Malaysian monkeys eating them fat rats. So if you have a rat problem, maybe you should get some macaques, because then you won't have a rat problem. You will have a monkey problem. Okay, right, enough. So what is this one? Okay, I'm just gonna read out for you. So this is Dusileo. Is laying Dusileo. Okay, what does it mean? It means would you like some? Okay, so you would add the subject in the front. So if I wanted to ask you, would you like some coffee? So coffee in Korean is kopi. So kopi dusileo. Okay, would you like some tea? Cha dusileo. Would you like some tea? Cha. Like Chinese, right? So yeah, just anything dusileo. Would you like some of this? Okay, but so in Korean the subject you put at the front. Okay, what is it in Hokkien? It is lu ai hami bo, lu ai blank bo. Okay, so you put the subject here. So you go, if you want coffee in Hokkien is kopi. So it's like in Korean, except you emphasize the p. Okay, so kopi, lu ai kopi bo. Would you like some coffee? Lu ai kopi bo. Or you can try tea. So tea in Hokkien is te, which I think is a loan word from English or Malay, because in Malay, tea is te. So lu ai te bo. Sounds a bit weird, but yeah. So lu is you, I is want. You want this or not? Right? Lu ai hami bo. Okay. So there you go. Kopi dusileo. Lu ai kopi bo. Would you like some coffee? Okay, simple questions. All right, and then you can go, aya means yes, I want. All right, that's how you respond. Or you can say, I means want, I or my, like a bit like in Thai, ao my ao my, no, I don't want. My in Hokkien is no, I don't want. I is yes, I want. Okay, or you can just nod your head or shake your head, whatever. Okay. Okay, so if I were to ask you, lu ai kopi bo, you go, aya, kam sia. Okay, yes, I want, thank you. Okay, all right, and what's next? Oh yes, so yeah, I've written down in more detail, like my own little scientific journal article, how to process some of this scientific papers. So if you like, you can hop over to the blog and have a read. But yeah, really, no, it's just whatever I said in text format. So you can find out a little bit more. I explain, what is beta propiolactone, all this stuff. Okay, so that's all from me. I hope you have a lovely weekend, and I will catch you. Oh, so yes, a lot of people, looks like a lot of businesses are getting back into action. At least if they haven't started today, they are gearing up to start next week. So hopefully we'll get some amount of normalcy. Okay. Now I imagine we won't obviously be back in full force, and it's not going to be the same. But I hope you stay safe, stay healthy, and perhaps I will see you or not. See you. Okay. All right. That's all from me for now. Da me bois. Sam out.